Hey everyone, welcome to this presentation on one of the most fundamental concepts in probability, the law of large numbers. I'm Sujal Manandhar and I'm currently studying in Sunway College, Bachelor's. So in this video, we'll explore how this law works, its type, mathematical intuition, real-world applications, and even a Python code. So let's dive right into it. So what exactly is the law of large numbers? Well, in simple terms, it states that as we increase the number of trials in an experiment, the sample average gets closer and closer to the expected value. Let's take an example. Imagine flipping a fair coin. The probability of hitting heads is zero point 0.5, but if we flip the coin 10 times, we might get 6 heads or even 8 heads, which is not exactly zero point 0.5. However, if we flip it 1000 times, the proportionality of hit will be much closer to zero point 0.5. You must be wondering, why does a larger sample size give more accurate results? Yes, this is the power of law of large numbers. Now let's talk about the two types of large numbers, the weak law and the strong law. The weak law states that as the number of trial increases, the probability that the sample mean difference from the expected value by more than a small amount approaches zero. The strong law, on the other hand, guarantees that sample mean almost surely converges to the expected value as the number of trials goes to infinity. In simple terms, the strong law is the stronger version that works in nearly in every scenario. So, what is the key difference between them? The key difference is that the weak law works in probability terms only, but the strong law ensures almost certain convergence. Now, let's get a bit more mathematical. The law of large numbers applies to a sequence of independent and identical distributed random values. We represent this as x1, x2 to the xn. So, let's break the formula. First, we have expected value Ex is equals to mean, and sample value Xn is equals to 1 by n summation Xi. Xi, or the summation Xi, is just the sum of all the individual outcomes like the number of hits, and n is the total number of trials. So the theory of large number law of large number ensures that when n, the total number of trials, goes infinity, the sample mean is the true actual value. This means that as the number of observation increases, the sample mean will approach the true expected value mean. So now you must be wondering why this all happen. The answer is statistics. As the sample size grows, extreme values cancel out, and the probability of larger dimension or derivatives from the expected value gets smaller. In simple terms, the more trials you conduct, the more balanced and predictable the outcome becomes. Now, the law of large numbers is not just a theoretical concept, it has real world applications in various industries as well. Firstly, in insurance companies. Insurance companies rely on law of large numbers to predict risks and set premium rates. In casinos and gambling, they also use law of large number concept to make to ensure that they always make a profit. And in stock market, investigators analyze long-term trends using LLN to reduce uncertainty, whereas in machine learning and AI, the more data we feed into a machine learning model, the more accurate its prediction becomes. This is the real life applications of law of large numbers. Now, want to try this yourself? I have code to simulate the law of large numbers. You can simply click code link over here and you will be directed to my code. I have already written the code, So I'll just summarize the code and I'll just run the code. First, we have imported necessary libraries. The first library is NumPy, which is used to perform numerical operations efficiently, and matplotlib, which is used to visualize the results through plots. Then we have defined the number of trials, representing the number of coins tosses and creating an array. Then we have simulated coin toss, where 0 is equals to tails, 1 is equals to head, and the simulation is for 10,000 coins. This will create an array where it will be random sequence of heads and tails, just like real coin flips. Then we have calculated the mean proportionality of heads, like computing the sums of heads and dividing it by the number of tosses to getting the running average or simply sample mean. Then we have plotted the sample mean over trials. Plot that figure 10,6 uh, sets the figure size for better readability, and we have plotted the proportionality of heads over time with the color blue, which makes the line better for better vision, and we have added a reference line for expected value, which draws a horizontal dash red line at y, which also represents the two probability of getting hits. Then we have added labels and title, where X level is the number of trials, Y level is the proportional of hits, and the title is the law of large numbers. Then we have created a grand and legend, which displays the level and which also adds a grid. And we have done the notation, noting the key idea. Then we have displayed the plot. Now I'll just run this code. So yes, as I run this code, it gave the result or the output. Now I'll just interpret the result in simple terms so that you can understand why I really do this code and what is the use of LLN. So now let's just analyze what this simulation tells us about the law of large numbers. At the beginning, a small number of trials, the probability of it fluctuated widely. Example, first trial must be 1.0, 100% hits or 0.0, 0% hits. And the fifth trial could be 0.4 to 0.6 or any other smaller variation. And then conversion as increases, which means that as the number of trial increases, the sample mean gets closer and closer to 0.5. By around 1000 plus trials, the sample mean becomes very stable. As you can see in the picture, we have the blue line which shows the stability of the line, and LNN in action. This also confirms that as the number of trial increases, the expected mean approaches the true expected value. No matter how many times we run this code, the simulation or the final proportional will always be stable around 0.5. So, as I said about the real world applications, this is why casinos always make a profit in the long run. In simple terms, uh, they might win or lose, but it is a win-win situation for them as they use the law of large numbers. So, what are the key takeaways from this code? So, from this code, we have learned that as trial increases, the sample mean converges to 0.5, which also confirms the law of large numbers in action, and it also ensures long raw stability even if short-term outcomes are random. So after this code, we have misconceptions. So before we wrap up, let's address some common misconceptions. Gambler fallacy. Many people believe that if a coin lands on heads 5 times, the next flip is more likely to be tail. But that's completely wrong. Each flip is independent. And second misconception is LLN is not for small samples. LLN not only works in the long term, but it is not for a handful of trials. And the third is LLL versus central limit theory CLT. LLN ensures sample mean convergence, while CLT explains the distribution of sample means. So, what did we really learn today? The law of large numbers is crucial in probability and statistics. It also ensures that sample average gets closer to the expected value as we increase the number of trials, and it has applications in finance, insurance, AI, and even gambling. This is the presentation of law of large numbers. Thank you.